Today's speaker is Bernd Heiselet, who is a senior research scientist at Honda in Cambridge, Massachusetts, and his talk will be titled Part-Based Multi-Feature Pedestrian Detection System.
All right, thanks Patrick for the invitation, and it's a pleasure to be here. I know the timing is not really great, so it's Friday afternoon, it's a long weekend coming up, and I'm also late, so sorry about that. Anyway, so I'm going to explain to you a system that I actually developed at MIT with a student. We have a collaboration with the Center of Biological and Computational Learning at MIT, and it's about pedestrian detection. But before that, I want to show you what we at Honda are working on. And probably most of you guys have seen this robot. It's Asimo, and we're developing in that group in Cambridge. We're working on the AI part and mostly the vision part of that robot. I see a couple of specs here, and they changed a bit. The maximum speed, I think, is it's much faster now. It actually can run, so it should be over 5 kilometers an hour. But what we actually work with is we have 2 cameras there and 2 color cameras, which we use for doing the vision part. Show you a couple of things that already exist on that robot to get an idea of what it can do. So here it actually recognizes a gesture, a pointing gesture, and you see it's gonna look at the point where the person pointed to, and it's gonna move there. So the idea behind this robot is, right now we have just a couple of demo applications, but later on we actually want to have a kind of service robot which can assist people and can do some useful tasks. Right now it's mostly you see in shows. It was in the Museum of Science in Boston. They're touring around there and giving shows. But hopefully we eventually get something really useful done on that, so that people might have actually a robot at home to help them. Okay, I think you get the idea. Let's see, there's obstacle avoidance, which is kind of interesting. So that's actually using the stereo camera pair to estimate the distance between objects in front of the robot. And you see actually it stops when it sees a person crossing when it comes too close. And it actually can avoid obstacles. So it walks around the person here. All right, and here is a simple application that, this video has been recorded in the main research lab in Wako in Tokyo. And that's a receptionist application. I think, it's like it's welcoming the person and then asking where the person wants to go. So it has some speech recognition on it too. All right. So let me show you what actually we are working on. So if a robot, if you want to have a robot at home, it has to be able to do a couple of things from the view of computer vision applications. It has to be able to recognize objects, and at least the most important ones, like you want to recognize a desk, you want to find the door, be able to leave the room, and also you want to obviously find any people if you want to communicate with people. So you want to determine the identity, and you want to recognize the gestures and the expressions. So that's basically what we are working on. It's in general object detection, but specifically we focus on things that are related to people. So we want to actually do person identification and also expression recognition. And now I'm going into a kind of approach that became really popular the last couple of years. And you find it often called part-based approach. I usually call it in my papers components, but Shimon Ullman call it fragments. Other people call it patches. And this is a general approach for object detection and recognition in video images. And I want to show you what most of these systems have in common. So now assume first a global approach, which is a standard approach where you have this pixel image, and then each pixel in your image is a feature. So basically, a feature is connected to a position, X, Y position in the image. Now, if you want to actually, if you have this new image here, and you take the same feature at the same X, Y position, you see it's not connected to the same part of the object, right? So it's shifted because the person's face rotated slightly. So what that actually means if you do classification is that you have large in-class variations if there are rotations of the object. And that will make the problem really hard. So if you just take each pixel as a feature and try to classify that, you want to make sure that actually there are no variations in the image, so that these pixels are actually in correspondence, which usually is not the case. So the idea behind the part-based approach is you first localize parts of an object and then take the features within these parts relative to the part you detected. So these X star and Y star are actually coordinates relative to the corner of the part you located. So now you try to locate the same part in this image, and then you look at the same feature here, and indeed it corresponds to the same part of the object. So what you try to do is actually solve the correspondence problem. So the features are in correspondence. That gives you small in-class variations, and that should lead to better classification results. That's the basic idea behind that. There are a couple of other things if you use parts instead of trying to do a global recognition system. Like you can better handle occlusions, partial occlusions. It has more flexibility in the geometry and so on. But this is the basic principle that all these systems have in common. Basically, you have a part detector which can move around a little bit, and then you take the features inside these parts and classify those. All right? And also, what you'll find is that these systems actually have two levels. And the first one is, what I just mentioned, is the detection of the parts. And there are lots of different ways of doing that, and I'll show you a couple of them later. But basically, let's say you want to localize the eye. So you have an eye detector that moves over the image and then finds the eye location. You do the same for the nose and the mouth. And in the second step, you actually want to see if there is a face. So in this case, it's a face detector. So you use the outputs of your part detectors and somehow combine them and determine if you have a face there or not. So you always find these at least two levels in these systems. There are a couple of biological systems that actually they divide parts into subparts, so you have a whole hierarchy there. So it's like you can have more than just two levels. But at least two you'll find. Okay, so here's here two principal approaches actually how to detect the parts. And I'm not sure how familiar you guys are with these systems. But one way is as an interest point based approach, where you first actually run an interest point operator on your image, which can be just a corner detector, and then you extract the patches around these interest points. And you can perform all kinds of normalization on these parts to get invariance against rotation. And I showed that here for two patches. So you extract these two patches. And during training, actually, you looked at the object, and you also extract these patches, and now you match them with a test image. And then you just find the matches, and based on that, you determine if you have seen this object or not, if you have seen it before or not. The other approach is you have a sliding window. So you actually don't compute interest points, but you slide a classification window across the image, and you analyze the contents of this classification window. And again, inside the classification window, you run your part detectors, and you try to localize parts. And based on the outputs of the part detectors, you determine if it's the object you're interested in or not. So as you can see in this step here, you remove most of the image in the first part. You just extract like 100 points and 100 patches, and that's it. That's pretty fast. While here, actually, you look at every pixel, and you also shift the object window pixel by pixel. So that's really slow, but it's more thorough. So here's a comparison of these two approaches. The sliding window approach works very well for low object resolutions. So you see the best phase detector, which is probably systems based on the Violite-Jones detector. They operate at resolutions of 19 by 19 for phase images. And at this resolution, actually, you can't find many corner points anymore. So all these interest point-based systems will fail, because it's just, at this resolution, you just don't get reliable detection of interest points. So that's why the interest point-based systems, they don't really work that well at low resolutions. But they are really fast, because you throw away 99% of the image in the first step. And you only analyze the patches around the interest points. Here, they're really slow. Millions of object windows have to be processed per image. Still, there are real-time systems out there, but especially if you have to deal with hundreds of classes, I don't think this is a really feasible approach in real time right now. The rotation invariance is problematic here. Basically, you have to, for each rotation you want to, if you have in-plane image rotation, you basically have to rotate the image and repeat the process over and over again. So that makes it really slow. Here, there are systems where you actually can have invariance, rotation invariance, by just performing these invariance operations on the patches you extracted, which are usually just a couple of hundred. So rotation invariance, scale invariance, that's relatively simple with these interest point-based systems. It's really hard to do with the sliding window approach. As I said, you choose a generic interest point operator. Most people these days use a corner point operator. The only thing you have to worry about is that it's kind of, you can repeat the performance. It repeats the detection. So basically, if you have the same object and you change the viewpoint slightly, you want to have the interest point operator respond to the same points on the object. So the repeatability is pretty important, but there are studies out there show basically can't go wrong with it if you use the Harris corner point detector. Here, you can choose any kind of detector to localize your parts. Matched filters, I used work with SVMs and so on. So you're pretty free in choosing your part detector here. Large number of parts possible. Here, not really, because you're limited to the number of interest points you detect. You'll find this mostly in detections. As I said, best face detection, best pedestrian detection systems operate like that. Recognition of large number of objects. Say if you read one paper, it's probably David Lowe's paper where you recognize, like, I think, around 1,000 objects using this interest point-based system there. What kinds of parts you want to choose? Here, obviously, you're limited to the parts around the interest points. Here, you can choose, you're free to choose any part of the object. So you can actually use machine learning techniques to determine which parts are important, which parts are characteristic for an object. So it gives you more freedom there. So anyway, each of these approaches has advantages and disadvantages, and it really depends on your application which one you want to choose. I didn't talk about the geometry right now. I just mentioned how to actually detect these parts. But you also actually want to model the geometry, basically the spatial relationship between the parts. And again, there are a couple of different possibilities of doing that. One way is actually you just completely ignore the geometry. Basically, you just look at the appearance. If you find the parts, if you find all the parts, it's good. You don't really care where they are and in which configuration they appear. So you'll find, especially Tommy Poggio, he did that in his biologically inspired model. he claims it's really hard actually in the brain that we have these geometrical models. So he says there is no geometry there. So it's pretty much all appearance-based. And then you can increase, kind of go up in the complexity of how you want to model geometry. You say, well, just model the geometry of the location of each part relative to a center point of the object, okay? So you say this part you would expect in this region. So just you can model it by a Gaussian or whatever. But you don't model actually the relationship between this position and the position of that part, right? So it's called a star graph model. It's relatively simple, and if you have m parts and n detections per part, you basically just have to evaluate n times m configurations here. Now, the most complex model is a fully connected model where you have relationships between all the positions of the parts. You'll rarely find that actually, because if you have n detections and m parts, you have to evaluate n to the power of m combinations, spatial combinations there. Yes?
At that point, the geometric model seems attractive. And they're used all the time in visual servo and other branches of robotics.
Say it again.
A geometric model seems attractive at that point.
Yeah.
Because it covers all the correlations between different views and the features that exist in them.
That's correct.
Plus it models occlusion and light and shade and surface.
That's correct. But look at that. I mean, so the thing is, if you run your part detectors, you get, let's say you look for the eyes, at a relatively low resolution for the eyes in a face, you might get a couple of thousand responses of your part detector where the eyes might be located in the image. So in this case, you would have 1,000 detections for this part. Now you have, let's say you have 100 parts. You have 1,000 to the power of 100 possible configurations, which you would have to evaluate which one is the most likely one, right? And you can't do that. So you want to have a geometric model, but you want to keep the complexity low. So usually you model the position of the parts as independent. So you just say, well, if you model the position of a part just relative to the center, but not relative to the other parts. So it's a pretty simple. You're right. I mean, you could have a sophisticated model. You just run into problems, into computational problems there.
Besides the star graph model, there are all these kind of flexible templates where you have a bunch of feature detectors that are tied together by springs or something.
Right. Exactly. That would be that. Right. That would be exactly that. And I would say if you pick a model, pick this one here. Right. I mean, that's my personal preference. I would say, rather go for a large number of parts and a relatively simple model than choosing a small number of parts and a relatively complex model. But again, it's like people would argue about that. So let me show you what systems are out there. It's a little bit simplified. And actually, I have to tell you, I stole the idea from Perona. So he had a similar graph there. It shows you the training samples you need for training your system and the number of object classes that you actually can recognize. So you see that I've been working on face detection actually since 2000. And you see that there are really good systems out there now for face detection. I think the problem can be considered to be solved. And they're good systems for pedestrian detection too. What they need actually, they need thousands, actually hundreds of thousands of training examples. So you need a ton of training examples. And what you can do is you can just distinguish between two classes, right? You say it's a face or it's not a face, it's a pedestrian or it's not a pedestrian. So it's two classes and a lot of training samples there. So you go to a David Low SIFT system, which is a one-shot learning approach. You take one image of an object. So you have one training sample per object. But you can actually recognize thousands of objects with that system, and it also works in real time. This one does not generalize, and I'll show you the generalization performance later. So then, probably most of you are familiar with the Caltech 101 and 256 database. So I think you have about, I'm not sure, like 40 or 50 around that samples, training samples per object class. And I think obviously in the 101 database, you have 101 classes. 256, you have 256 object classes. There are systems out there, actually, you can read papers about on all these systems there. So if you look at the generalization, and a generalization, I mean generalization across a class of objects. Here, if I say you have one object, I mean you really recognize only this specific object, so it's not a class of objects. So if you show it a cup, it just recognizes this cup with this specific pattern on it, but it doesn't recognize any other cup. So there's no generalization there, basically. And the generalization increases as you go down here. These systems generalize very well, so pretty much work on any phase on any pedestrian. So what I would say about the applicability, this stuff works in real-world applications. So if your goal is to recognize a specific object, or lots of specific objects, yeah, just go with that system. This one, I'm not really convinced about this. You know, they're mostly academic papers there. I mean, they claim they work on 101 classes, where one class is like chairs, and I know that nobody solved the problem of recognizing chairs, right? So the performance on this, you have to take with a grain of salt. I mean, I would say these systems are not, you can't really use in, I don't know of any real-world application where they can be applied to. This stuff works very well, you know, face detection, pedestrian detection. Just plug it in if you need it, and it's fine. So the question is how you make actually these things your work. And I think you probably need more data. I mean, people claim, you know, the goal is to train on very few training samples, like just 40 images of chairs and be able to recognize chairs. I would say that's not possible. So somehow you need to collect more data. You probably have to develop learning algorithms that are more capable of dealing with large number of samples. And training time is an issue, right? Obviously. So here's what I say, and you know, it's like you'll hear other people say different things. Despite the trend you see these days in the papers, you know, working on large number of object classes, training on few samples, I think it's not possible actually to train a system from a few number of images to be able to reliably recognize a complex object class. And complex, you know, I don't even mean as complex as the class of chairs, which is super difficult, right? Because chairs vary in appearance. You know, it's like, I would say faces already are relatively complex, but most people would consider them as a simple class of objects. I think it's not possible, period, right? So I think you can, from scratch, I mean, a system that doesn't know anything about computer vision, it's just a machine learning system. You show it 40 images of chairs and say 500 background images. And from that, it's able to recognize chairs in the future. I don't think it works. So as I said, what we need is maybe machine learning techniques actually for large training sets which operate in high-dimensional space. And usually in computer vision, you have high-dimensional space because you work in pixel space, or you know. So that's, I think, what we need. Or otherwise, you know, if you want to be able to train on a small number of training images, you need a system that has some information already, right? That has some capabilities. It's you know, people often say, well, humans are able to recognize an object. You show it only twice or 3 times, and they can recognize it. It's true, but we have a lot of experience. We have a huge computer vision machinery that does segmentation. We can recognize, you know, shape from shading. And that's stuff that we already have. We don't have to learn that anymore. So if you want to be able to train on small training sets, you know, you need a system that already knows a lot. And I don't see any of those systems around these days. But, you know, who knows? Maybe we have one in 20 years down the road. So anyway, let me come to our system here. It's actually pretty simple, and you know, I want to keep it relatively simple because I want to keep the option open to implement that in real time. And here's the basic idea. So you have an object, you put a grid on it, and basically that's my geometrical model. So I confine each part to be within a grid element. That's basically the geometry. And then what you do is you have some parts which are assigned to grids. You just localize them in that image by doing normalized correlation. And you pick the maximum value of the detector inside that grid element. And let's say if you have 500 parts, you get 500 output values, and you use them in a combination classifier, which tells you if in this object window the object is there or not. So that's basically it. So it's really simple. I mean, the time-consuming part here is the normalized correlation, which, there are lots of different ways of doing that efficiently. You can use special hardware. So that's basically a technique well known from template matching. So the interesting part actually is how do you determine the parts, so how do you do the training, how you build the classifier. And what we do is we first compute what we call feature maps. So basically any kind of, it's like what you think would be a useful feature. You could just use the gray values as they are. We use gradients, and we use the responses of Gabor filters. So you compute these feature maps for your training images. You apply this grid to each of these feature maps, and you randomly extract a ton of parts. You can extract at different sizes or whatever. It's like in the hundreds of thousands of parts you extract from your training images. What we do then, a step to kind of reduce the number of parts we have, is we cluster parts which belong to the same grid element. It's just a data reduction step. And then these cluster centers we found, we correlate with the training images. Again, each part is just correlated within its corresponding grid element. So from that, we actually get the maximum correlation values for each part, which is actually the feature we derive from a part. So once we determine the part, we apply it to each of our training images, and it gives us one output value, which is the maximum normalized correlation within its corresponding grid element. So we still have too many parts there. So what we do is we use gentle boost actually to iteratively select parts that are useful to discriminate between the object and the background. So that's a two-class problem here. Okay, so that's basically how it is. So you have a huge pool of parts, and then you iteratively select the ones that you think that the classifier, gentle boost classifier, thinks are useful for solving the problem, the classification problem. So that's pretty standard approach, and I think lots of people do it now more or less with different variations. But it's surprising how well it does, actually, if you compare it on, to other systems, more complex systems on standard databases there. So what would you do in the test case? Now that you found your parts, again, you apply the grid to the test image. You correlate each of your selected parts with a test image inside its corresponding grid element. And you get this maximum correlation. You just put it into your boosting classifier. It will give you a value which tells you if the object is present or not. So that's all there is to it. Now here's a couple of interesting things. These are experiments on a pedestrian database that gives you an idea actually of how many parts we need. So this is the gentle boost performance on a training set. We iteratively select here parts. It goes up to 500 parts, and this is the training error. I think it's just, we start with 5,000. We had 5,000 images there. And then we looked at the performance, and you see it's pretty much with 500 parts, you don't make any mistakes there anymore. So now how does it translate on the test set? You see it's like there is not really much overfitting going on there. You improve performance all the way up to 400, and from there on it stays pretty much the same. The training error goes down a little bit, but the test performance stays the same, but it doesn't get actually worse. So there's no overfitting, really. What does that tell you, actually? It tells you that, especially in this problem where we operate, I think the resolution of these pedestrian images was something like 50 by 100 pixels, so it's relatively low resolution, that the individual part detectors are not super reliable. So you're not going to get away with just picking 5 parts and trying to detect pedestrians there. So what you instead need is you need a ton of parts there. And so here's a conclusion. with few parts and a relatively small part size. Our part size was like 5 by 5 pixels. That's because the objects themselves were relatively low resolution. You'll not get a good performance. So most of these systems who claim they can detect objects using just 5 parts, it's like maybe they can if the object is super high resolution and they can find some detail which is always the same in this object. But if there are lots of variations in the object, like pedestrians that change their clothes, it's like size, and you're not going to get away with a small number of parts. All right, so features, I told you we computed different feature maps. And the first thing, of course, everybody tries is just using the gray values here. So our parts here would just be parts of the gray value pattern. The next thing you try is the magnitude of the gradients. It's basically kind of edges, and which is really what became really popular these days, is Gabor wavelet responses. Just because it seems like biological systems kind of rely on these kind of features here. Okay, so that's what we tried. Gray gradient and Gabor, and we extracted parts from each of these maps and looked how the performance is. This is an ROC curve. This tells you basically how good the classifier is. Further up, it's better. This is the false positive rate, correct recognition rate. And you see that the individual features all about bunched up here, they're all about the same, right? So there's no big difference. But if you combine them, if you throw all these parts together, you get better. And unfortunately, people usually want to know which feature to use. And I say, well, it depends very much. And usually you're better off using a lot of features, right? And there is no real recipe how to pick the right features except for doing experiments and trying it out. That's all I can tell you. It's kind of black magic. There's not one single set of feature which I would say is the right one for computer vision. So you get a significant actually increase in performance by just combining those features. So what was kind of interesting and in our experiments is that usually people, if you want to say you want to detect phases, you would say, well, look for, if you extract the parts you want to use in your classifier, say just look at phases and try to find parts which occur in phases and ignore the background class. So when you train your part, when you select the parts, you would just look at the positive class, so to speak, right? And that's what people usually do. So when you do the part selection, they just usually take the positive class in a detection case and ignore the background class. It turned out actually, so if you have a part of the, in our case, of pedestrian, and you correlate it with the pedestrian images and with the background images, and you build a histogram, you will see something like that. So the correlation in average for the pedestrians is higher there than with the background. That's exactly what you want. So it has some discriminative value, this part. So you are able to discriminate pedestrians from background based on this part. So that's how a histogram typically looks for if you extract it from the positive class. Now what we figured out actually, we also extracted parts from the background class, and the background class in our case is just random background, right? I mean, it's like just street scenes without any pedestrians in it. And then occasionally you find parts that have a distribution in the correlation histogram that looks like that. So they correlate higher with background than actually with pedestrians. So that means these parts are absent in pedestrians usually, but you find them frequently in background. And they also have a value, right? Obviously, you can use them to classify, distinguish between the two classes. And that's was kind of surprising. I think that people didn't do that before. So it helps if you add the negative class to your training data when you actually try to find useful components or parts. Actually, if you look at these parts selected from background, there's 5 by 5 parts, so you can't really tell, is that extracted from a pedestrian or not, so they don't tell you anything, right, just looking at them. But we figured out if you add these background images to the part learning stage, your classifier performance increased by 5%. It's actually quite a bit if you're dealing with detection problems. So 5% is a lot. So I would suggest, if you take an approach like that, just always use the background, the negative class too. And here is a graph actually that shows you how positive and negative parts, where they come from. And what I mean as a positive part is a part that correlates more with the pedestrian class than with the background class. And a negative part would be a part that correlates more with the background class than with the pedestrian images. You see actually that you actually get negative object parts. So you actually get parts that were extracted from pedestrian images but still correlate more with the background class than with the pedestrian class, which is kind of surprising. On the other hand, you get positive background parts. So you get parts that were extracted from the background, but they have higher correlation with the pedestrian images than with background images. And that kind of shows you how the relationship between these 4 different kinds of parts are as you increase the number of parts in your training set. It's kind of interesting to see that. A little bit surprising. So anyway, here it is. I mean, we tried it on this pedestrian detection data set that was published in 2006 in a PAMI paper by Mundo and Gavrila. And they tried a ton of different classifiers there. Support vector machines, nearest neighbor, k-nearest neighbor, and so on. And they also had a couple of different feature extractors there. And it turns out that our system with 500 components and 3 different types of features performs better than any of their systems there. So you get really good results. And we trained on face detection. We trained on detection of objects in an office environment. And pretty much in all these tests, we got the results that are as good as the best systems out there, or even better. All right, so let me summarize the presentation. I showed you 2 different types of part-based approaches. One is with the interest points. The other one is with a sliding window. I mean, I implemented the sliding window approach, but for other applications, you might want to use the interest point-based approach, which can deal with a large number of objects. It's much faster, but it's not as accurate as the sliding window approach, especially if the resolution of the object is low. I would say, choose a large number of parts, small of medium size for highest accuracy, and small, medium size relates to the size of the object in general. It's like maybe a quarter of the size of the object. Keep the geometrical model simple, otherwise you're not able to use a lot of parts there. Our system is flexible in the type of feature. You can pretty much generate any arbitrary feature map you want and extract parts from that. You can choose a flexible part size, and the number of parts is flexible too. We hope we're going to put that software on the MIT webpage soon, so you guys can actually download that and do your own experiments if you want. We got state-of-the-art results on several detection and recognition tasks there. The last one I showed you was actually on pedestrian detection. It's conceptually really simple. It's just basically template matching with a large number of small templates. So you could, if you really want to, you can do that in real time if that's your goal. So the potential is there. And that's pretty much it. So if you have any questions.
It's fast only on kind of low resolution subjects. It would seem natural to use a multi-resolution.
We actually, what you do is you use a multi-resolution approach, right? I mean, basically, to achieve scale invariance, what you do is, there are different ways of multi-resolution approach. So there's like, you could possibly train different classifiers on different resolutions. So you basically cascade them. So you use the low resolution classifier first to eliminate large parts of the background. And then you go, as you decrease the number of image parts you look at, you use better classifiers. That's definitely And I implement a system like that for face detection, and that helps. If you look at Viola Jones, it's slightly different. He has a cascade too, but he has a feature cascade. So he just starts with very few features he looks at, which he thinks are important for face detection, removes background parts, and as he goes up the cascade, he adds more and more features, and the classifier gets slower. So that's a slightly different approach. So that's not really resolution-based, it's feature-based. But yes, that's definitely what you would have to do if you want to have a real-time system. You have to do something like that. That's right.
I don't see how this achieves a rotation variance.
This doesn't achieve any rotation, and I never claimed that. So if you want to, so what? Well, so here it is. There are different types of rotation, right? So there's in-plane image, in-plane rotation, and there you would look at David Lowe's system, which uses SIFT operators, where basically first you find the interest points, you compute a main orientation around these interest points, and then based on that, you normalize the patch. That's not possible in that system, obviously, right? Because we have a continuous part detector, so we can't normalize at every possible location. So what people do here, you will see a rotation invariant phase detector, which runs on a sliding window, uses sliding window approach, which is also invariant to rotation depth, actually. And they implemented that. So it's rotation in image plane and in depth, and it's real time. And they just train different classifiers. That's what they do. So you would have for possible, so it's like you somehow discretize, the 360 degrees in a couple of steps, and you train different classifiers on that. Alternatively, you can just, well, actually what you do actually is you rotate the image. I think you use the same classifier, just rotate the image. For rotation depth, you really have to train these different classifiers, right? It's just, you can't just rotate the image and run the same classifier. But yeah, it's not easy to do. But then people in biology claim that our system is not rotation invariant either, right? So maybe you don't really, you really store different views, right? So you basically have different classifiers. It's up to you if you believe that or not.
Combining different features like edges and algorithm Gabor filters, do you actually just add them together, or?
No, what we do is when I say feature combination, what we do is we calculate these feature maps. So you do a convolution, right? So you choose whatever operator you want, or you compute the magnitude of the gradient. You generate a new image. Instead of the gray image, you use that to find parts in there. And then at runtime, you would again first compute these feature maps, and then you correlate the parts with the corresponding feature maps. So you don't really throw anything together, right? I mean, it's like, so you don't mix up, different features with different, parts, and so it stays all the same. Yeah, there was another question.
I was curious about a couple of possible comparisons. You said that this benchmarks pretty well against existing systems. There are a couple systems in particular that I'm curious about. One of the vision workers here, Andrea Plum, mentioned that the state-of-the-art pedestrian detector had its performance boosted substantially by a pre-process based on Derek Hoyam's photo pop-ups, a simple geometric estimate of vertical and horizontal surfaces.
Oh, right. Yeah, that's right. I'm not. I think that paper was published in kind of context recognition. So it's true. I mean, there are tons of, I worked at Daimler Chrysler for a long time. It's like, 10 years ago, and they estimated the ground plane, using stereo, and then they just looked for pedestrians on the plane basically, and said, well, obviously that's better than just looking for pedestrians in the trees, right? I mean, I would call that a trick to improve the performance. So that.
In a way, that's a trick to perform. It's a trick if it's improving the performance of a particular classifier.
Right.
Geometric context improves all your classifiers at once. That's the second comparison I wanted. I wanted this compared against Stanley Gillespie's work in Kojak, the street scenes.
Oh yeah, I was working with Stan for a long time. I'm in the same group basically. My student was working there. I would say these systems, he used a biologically inspired system, but he just used the first level of it, which is very similar actually to what we do. So it just used slightly different features, but basically it's the same thing. just that we don't have this claim that it's biologically plausible. So I just use any kind of feature I want to. But it is pretty much the same thing. And
it wasn't so much the biological plausibility that I was curious about as more the geometric context.
Right.
To understand the whole scene.
Right. Yeah, he uses that too, actually. And, I would say this context recognition thing, sometimes I would say the context is much more difficult actually to determine than the object itself. I mean, you will find applications where it's really hard actually. What seems easy for us to say, we're indoors or we're looking at the scene where, that's in the back and the car's there. It's like sometimes it requires a lot of processing actually to do some useful context recognition, right? And the simple object recognition task, the object recognition task you want to solve is actually easier to do than the context recognition task. I agree, I mean, if you're interested in a certain application like pedestrians in street scenes, then yeah, why not use any information you have available to make it better, right? To eliminate false positives. It's not my goal right now, right? So I'm not looking at these techniques, but I would say it is definitely a promising approach, right? I mean, I prefer data sets where you have actually, and that's why I took this one, where you have extracted patterns. So where they don't give you a whole image and say a full image and say, well, just see if you can find the person in there. Because there are lots of tricks, actually, how you can make your system work better, right? If you say you have a sliding window approach, you count the number of detections around the same position, and based on that, you make a decision. So it's really hard to compare the systems just saying, OK, is this classifier better or that? Actually, a lot of it depends on how the person implemented the sliding window approach, the scaling, different image scales, and so on. And I worked a lot on face detection, and that always made it difficult to say which system is better or not. And then many people use bootstrapping, so that they use tons of background images to bootstrap their data, so they use actually millions and millions of background images or patterns to increase the performance of their classifier, but they don't provide that in the training data, so you don't really know what they trained on. So this set gives you exactly the training set and the test set extracted, so there's no sliding there. You know exactly this is your pattern, so any machine learning guy can just simply apply it, doesn't have to know anything about computer vision, and just run his algorithm on it and see how well it does. All right. Thank you very much.